Okay, thanks everybody for coming. Our speaker today is Michael Hahn from Columbia. Mike got his start at Carnegie Mellon, which is actually where I went to undergraduate as well, and then went from there to Columbia to get a PhD in the Applied Physics Division, doing plasma physics and other important and interesting things, and then realized the actual excitement in this world is all astronomy, not in that tedious little plasma physics world where there are jobs and funding and money and all that. So he made the switch over to the Department of the Astronomy Laboratory, the Columbia Astrophysics Laboratory, where he's been working with Daniel Savin there, doing a range of activities. So I first met him when looking at his results on calculating ionization rates. Not calculating, actually measuring. One of the few people who does laboratory astrophysics measurements. So if you're interested in things like what the ionization balance should be for your hot cluster plasma, he will have some answers for you. The short answer is that things are pretty good but not perfect. Then he has also been working on observations of the sun and understanding what's going on inside the sun, which is what he'll be talking about to us today. So, in fact, I believe one of the most famous problems in solar astrophysics, which is what exactly is heating that corona anyway? That? Thanks very much.
Okay, thank you. So, thank you for inviting me to come here and talk to you today. It's been a very nice visit. And okay, so I will talk about some observations that we've been doing, looking for evidence for wave heating of the solar corona. This is work that I'm doing with Daniel Savin at Columbia, and our support has come from the NSF for this. So I will begin with an introduction to the coronal heating problem and the role of waves in that. And then I'll describe our methods and observations and results for a coronal hole region. So a coronal hole is a region where the magnetic field lines are open so that they are the source of the fast solar wind, and the field lines are open in the sense that they extend far out into the heliosphere, so plasma can kind of just flow out along the field lines. And then I will describe some results from a quiet sun region. So this is where the field lines are closed, so you have 2 foot points, and it kind of forms a loop. And this makes up kind of, in solar minimum, the parts of the corona that are not near the poles. And so we do find evidence for wave heating and that the waves are dissipated, so you need to take the energy out of the wave. So finding the wave dissipation is kind of the interesting part of this. But there are questions about what physical process actually causes the wave dissipation, and we have some ideas for a laboratory plasma experiment to look at those possible processes. So let me begin then with the coronal heating problem. So you're probably familiar with what this is, but if you're in the photosphere, the temperature is a few thousand Kelvin, and then in the corona, the temperature is 1,000,000 Kelvin, so you have this sharp transition region between the chromosphere and the photosphere and the corona above it, and there's also a decrease in density associated with that. And so the problem then is that you need some non-thermal heat transport mechanism to increase the temperature of the corona to the 1,000,000 Kelvin that is observed. Because the corona is not very dense, there actually isn't so much energy needed for it. It's only about 0.01% of the sun's total energy output to do the heating. The problem is finding a mechanism to bring that power into the corona. And the energy source is also believed to be pretty clear. It's the turbulent fluid motion that you see in the outer convection zone that you see in, for example, the granulation in the photosphere. So what this fluid motion does is the sun is permeated by magnetic field lines that extend from the photosphere, from the surface of the sun out into the corona. And all this fluid motion jostles the magnetic field lines around, and it can give energy to the corona by one method is that it rearranges the magnetic fields into configurations that are stressed, and then this process called magnetic reconnection occurs, which releases some of the energy stored in the fields and does the heating. Or you can generate waves. You wiggle the field lines, and then that causes a disturbance that propagates up along the field line into the corona, and that carries energy with it. And when the energy is dissipated, it does some heating of the plasma. So it has long been a problem which of these is the most likely scenario. And so to illustrate this, we have this paper from 2010. Can the solar wind be driven by magnetic reconnection? So driving the solar wind is very closely related to the coronal heating problem. A lot of the fact that you have a solar wind is because the corona is hot, so basically the thermal pressure pushes the solar wind out, and then you get some additional pushing on that from waves and so forth. But so this is a related problem. And they say it is unlikely that the slow or the fast wind is driven by reconnection. Okay? And then the same year, there's this other paper, demonstration that the solar wind is not accelerated by waves or turbulence. So this is obviously a bit controversial. Which of these is really important? So I'm going to focus really on the wave perspective of things. And this wave heating theory has a lot going for it. Waves are found throughout the corona. We see them in the chromosphere, in the transition region, in the corona itself, and even out into the solar wind. So there are definitely waves around. The problem then is that you need to dissipate the waves in order to get the energy out of them and heat the plasma. This has been thought to be difficult because what you would usually think of as dissipating the waves is collision, so the plasma viscosity and resistivity, but those require length scales of a few solar radii. And the problem with that is that once you get to a sufficiently large height above the sun, about 2 solar radii, first of all, the density goes down, so you don't have very efficient heat transport backwards, and also the solar wind becomes supersonic, and then you also cannot transport the heat backwards because it's flowing out faster than it can flow back. So that would prevent downward heat conduction to fill the whole corona with a high temperature plasma and create this sharp transition region. So we need a way to dissipate the waves relatively close to the sun. So now let me describe an observation that we did of a coronal hole where the objective is to see whether we actually can find evidence for wave damping, and then we'll worry about what causes it later. So we used data from the Extreme Ultraviolet Imaging Spectrometer, ICE, which is on the Hinode spacecraft. It's been in operation since 2006, and it observes the extreme ultraviolet with quite good spectral resolution. It's a slit spectrometer, so you point your slit at where you want to observe. So this background image here is an EIT. It's an ultraviolet image of the sun, and this is not what we used. This is just to show you where the spectrometer was pointing, and the spectrometer was pointing with the slit along where these white lines are. This is a coronal hole here. It's called a coronal hole because it's less dense than the area around it, so that's why it looks dark. And so we sum these 4 observations of 30 minutes each, and they go down to 1.44 solar radii, which is a bit below the bottom of this image. So every point along this slit has a spectrum associated with it, and so in every one of those spatial pixels, there's a spectrum that looks something like this. So this is a intensity versus wavelength. This is just a part of the spectrum, and you can see the different spectral lines that you have in the corona. So in ICE, it looks at a lot of iron lines. In the coronal hole, you'll typically see iron 8 through iron 12 or maybe 13. And then there's also some silicon and sulfur lines in there as well. So what we're interested in for looking at the waves is actually the width of these lines. So this is a zoom in on one of these spectral lines. So this is the intensity versus wavelength again. And the histogram here is the data. And to get the line width, you fit a Gaussian to this data, and then you can fit that and determine the characteristic line width. There's also an instrumental width that needs to be subtracted to get the actual line width out. And after you do that, then the line width that you measure is proportional to the ion temperature and this non-thermal velocity. Now, the non-thermal velocity is the part that's kind of directly related to the waves. It's proportional to so that the mean square wave amplitude is 2 times the square of the non-thermal velocity. So this is, there's a wave and it's kind of sloshing the fluid around, and so it's causing Doppler shifts that you're integrating over in time and space, and this causes a line broadening. And so that's the amplitude of the waves there. The ion temperature is also interesting from a wave perspective because it's affected by the heating. So if you look at larger heights, you can see that the minor ions are heated quite strongly. And So the ion temperature actually gives you some information about the waves, but I won't really focus on that too much in this talk, except to tell you about how we subtract the ion temperature part in order to get the non-thermal velocity part of the measurement. So we want to look at these wave amplitudes and determine whether we see wave damping. So what we can do is figure out what the amplitude should look like if the waves are not damped. So we can get this from energy conservation. So the energy flux carried by the Alfvén waves goes like this. You have flux is 2 times the non-thermal velocity squared times the mass density. And then these waves propagate at the Alfvén speed. So this gives you an energy flux. So this is mv squared, that's an energy, and then you have some speed, and that's the energy flux. And the Alfvén speed is proportional to the magnetic field strength divided by the square root of the density. Now, if the waves are undamped, then the energy flux crossing some cross-sectional area A would be a constant. And so you could multiply this times A and substitute the expression for the Alfvén speed in, and you would get an expression that looks like this. And then we also know that for a thin flux tube, the magnetic field strength times the cross-sectional area of the flux tube is also constant. So this is, as the magnetic field strength decreases, the magnetic field lines get further apart so that you have B times A as a constant. So then this part is supposed to be a constant if energy is conserved, and this part is a constant because you're traveling along a flux tube. And so that means that the non-thermal velocity should go as density to the -1/4 if the waves are conserving energy. So what we can do then is, if the waves are undamped, since the density is decreasing as you go to larger heights above the sun, we can look and see that the non-thermal velocity increases with this proportionality or not. So the other issue, before we can actually do that, is that we need to separate the non-thermal velocity part from the ion temperature part. So we can express our line width as an effective velocity, which has the part that depends on temperature, which we can call the thermal velocity, and then there's the non-thermal velocity. So to separate these two things, we'll make some assumptions. The first assumption is that we'll assume that the ion temperature is constant with height, at least at low heights to start with. And in that case, if that's true, then the changes in the line width, that is the effective velocity, depend only on changes in the non-thermal velocity because the thermal velocity is constant. The justification for making this assumption is based on the collisional heating and cooling times. So not the collisional heating time, but the heating time and the collisional cooling time. So the protons are not heated strongly like the minor ions are expected to be. So collisions between the minor ions and the protons cool the minor ions. So here what you have is the time scale for heating in the solid line and collisional cooling between the minor ions and the protons in the dashed line. And this is from a theory by Landy and Kramer. And this is height above the surface of the sun. So sometimes I show height versus from sun center and sometimes from the surface, but in this case it's from the surface because I took it from their paper here. So what you have is at low heights, below about 1.1 solar radii, you have cooling by collisions, happens on a shorter time scale, so faster than the heating of the minor ions. So okay, so this should keep the minor ions from having much of an increase in temperature with height. This eventually becomes invalid because you can see that at larger heights above about 1.2 solar radii or 0.2 solar radii above the surface, that the cooling time scale is slower than the heating time scale. So at that point, the minor ion temperature is expected to increase. So that's the first assumption. The second assumption is that we'll assume that the waves are undamped at low heights. At least up to a certain point, this has been observed. So this is based on measurement. So here's an example from our work. So this is the line width versus height, distance from sun center, the radius. And the points are our data, and this solid curve is a density to the -1/4 fit. So you can see that at least at low heights that this fit looks pretty good. And that's been found by many other people. So for a long time, if you only look up to about here, then you would say, okay, the waves are undamped. So this is the assumption we'll make in this low energy, in this low height region. So if the waves are undamped, then the ratio of the non-thermal velocity at one height to that at some other height just depends on the density ratio between those heights to the -1/4 power because of that proportionality we had. And we can measure the density independently. So this is density versus radius, and the densities here are from an iron 9 line intensity ratio, and we have those up to about the limit where this assumption is thought to be valid, so a bit above 1.1 solar radii. And so that's our measurement. And then you could, later we'll want to extrapolate this to larger heights. And you could extrapolate this in two ways. One is that you just have a scale height fit. So this is like what you expect for a hydrostatic equilibrium. Of course, the corona has a bit of an outflow, the solar wind associated with it, so this is not quite right. So we could also look at the kind of function that they get from white light density measurements using coronagraphs that go to larger heights. And such a function agrees pretty well with the just an exponential decay in the height range that we're looking at. So what we actually use is this functional form from the white light coronagraph measurements, which we've scaled to match our data at low heights. But we don't think that choosing one or the other of these methods would incur much error in the density because they're so similar. Okay, so we have the density, and now what we can do is we can fit the measured line widths with two free parameters, which are the thermal velocity, which is constant in the low height range, and the non-thermal velocity at one particular height. It doesn't matter which height this is, because all of the changes in the non-thermal velocity are determined by changes in the density, but we picked it to be 1.05 solar radii, so we're sort of in the middle of this low height range. And then we can fit our data and determine these parameters. So here's an example of such a fit. So this is the line width versus height again, and we have our data and the fit. This fit, in this case, gives a thermal velocity of about 26 kilometers per second and a non-thermal velocity of about 32 kilometers per second. This is for data for iron 11. And if you were to look at larger heights and see how this continues, then this fit would keep going this way, but the data kind of fall off of it, which is an indication that the waves are damped. So you don't follow this density to the -1/4 dependence. But that's just the line width, so we want to look at the actual non-thermal velocities and to estimate the amount of damping. So to do that, we want to kind of extend our assumptions to larger heights to continue separating the thermal and the non-thermal velocities. So the fit used up to 1.12 solar radii. And to extend, we're going to assume that the ion temperature continues to remain constant. Now, I said before already that the ion temperature probably increases at large heights. So this is, we know this is probably not a very good assumption at some point. But it's not too bad for us, because that means that in deriving the non-thermal velocity, we're not subtracting enough thermal velocity. So we're overestimating the non-thermal velocity. So if our goal is to look for damping, and we see it, then we're actually underestimating the amount of damping, because we should be subtracting more of the thermal part. So now I can show you the result for the non-thermal velocity versus height. So the different colors on this plot are results from different ions. So silicon 7, iron 9, iron 10, and iron 11. And this black solid line that connects the dots here is the average. And this dashed line is the density to the -1/4 trend you expect for undamped waves. So you can see that the waves are damped somewhere beginning around here. One other thing that I want to point out about this plot is that all of the lines have the same non-thermal velocity. So we didn't make an assumption that they would have the same non-thermal velocity. This came out of the analysis, and that's what should be true if the waves are causing the non-thermal velocity. So it's a fluid motion, it's moving all of the ions in the same way, so we should get the same non-thermal velocity. So this gives us some confidence that the analysis worked. So now we can try and turn this non-thermal velocity into an energy flux and see how much energy there is carried by these waves and where this energy is dissipated. So these are the equations before for the energy flux. And we get the mass density from the electron density times the proton mass times a factor of 1.15 to account for some helium there. And then for the magnetic field strength in the coronal hole, we used an empirical model from a paper by Cranmer et al. They described the magnetic field strength in terms of an area expansion factor, so that the magnetic field is related to this area ratio. So we need to normalize that by some base magnetic field. So we take this to be 7.3 plus or minus about a Gauss from these measurements by Wang 2010. So if we put all that in, then we would find an energy flux versus height that looks like this. So the points are again our data, and the dashed line is if the waves are undamped. Now in either case, the energy is decreasing the energy flux is decreasing, and that's because the magnetic field strength is dropping, so the cross-sectional area is increasing. So we can correct for that by multiplying by this expansion factor, and then we get a plot like this, in which the F times the area, so this is the thing that should be conserved, would be a horizontal straight line, so that's the dashed line, and the points here are our data. So you can see that, so that there's actual energy dissipation, and it's not just being spread out over a wider area. We fit this with kind of just an empirical kind of function, which is a constant up to a certain height, and then this height is a free parameter, and then that turns into an exponential decay. And this allows you to get some parameters out of this that might be meaningful. Now, this is just an empirical kind of fit. If you had some actual theory for what damps the waves, then you could put in some kind of physically motivated fit and learn something more specific. But since we don't know what damps the waves, this is kind of the best we can do for now. Yes? Yes, yes. The field lines expand super radially in the coronal hole, so they're not exactly. I don't think that's, no, I think that the expansion factor is larger than that. So if you have the coronal hole, then eventually the field lines extend so that they come down to the current sheet. So they go from the edges of the coronal hole down almost to the solar equator. So eventually they. I think they were like 2 or 4 here. I mean, you can figure it out by comparing this plot to this. So here's the last one that's part of the. So this is 4, and then this is 6. So like 2, I guess. So okay. So right. So this level of the horizontal line is the would tell you the amount of energy input from the waves going into the corona at the base. So this turns out to be 6.7 times 10 to the 5 ergs per centimeter squared per second, which I guess is 670 watts per meter squared, if you like those units. And the heat damping sort of turns on at 1.12 solar radii, and the damping length scale is about 0.2 solar radii, so quite short. You could also, if you had a model that tracks the waves in time, you might be interested in what the damping is like in time. So if you were traveling with the wave, this would be a time scale of about 70 seconds for the damping. So it's been estimated that to heat the coronal hole and accelerate the fast solar wind, you would need 8 times 10 to the 5 ergs per centimeter squared per second. This is kind of a classical estimate of how much energy flux would be needed. But in the 2007 solar minimum, the solar wind was weaker. It was a little less dense and a little bit slower than in previous solar minima. So it's been estimated that you would only need about 6 times 10 to the 5 in the time in which our data come from. And we measured 6.7. So it would appear that waves carry and dissipate enough energy at low enough heights to heat coronal holes and accelerate the fast solar wind. So there's good reason to believe that waves heat coronal holes, and now we're interested in seeing whether waves can heat quiet sun regions. So these are the closed field regions. Here's an example of an observation in which they've actually observed the waves in the quiet sun. So this is from an instrument called the Corona Multi-Channel Polarimeter, or COMP. And what it does is it measures line profiles with quite fast cadence, I think about 10 or 20 seconds. And what they measure is actually the Doppler velocity. So going from dark to bright here is showing positive and negative Doppler shifts of the lines. And what you can see if you look along some of these loops is that the color shifts from darker areas to brighter areas and then back to darker areas. So you see evidence for oscillations along these loops. And if they have a movie that you could play, and you would see these oscillations actually traveling along the loops. So there definitely appear to be Alfvén waves in the quiet corona. But the amount of energy in them is difficult to tell from these Doppler shift measurements. If you look at the scale here, it goes from -1 to +1 kilometers per second. And actually the level of the grayscale here is more like +0.5 to -0.5 kilometers per second. Whereas in the line widths, we were inferring 30 kilometers per second amplitudes. So that's probably because when you integrate the Doppler shift along the line of sight, a lot of the shift gets washed out, whereas with a line width measurement, you might be able to better quantify the amount of energy in these waves. So that was part of our motivation for studying this, was to actually see how much energy is in them and if they're dissipated. So we took an observation of this region here in this box. So this is, again, just a background image of the sun from the time at which the observation was taken, also during the solar minimum. Again, our observation came from the ice spectrometer. And so we want to trace the evolution of the waves along the magnetic field. And it's a bit hard to tell where exactly the magnetic field is in this image. And it's a bit harder in the ice data. So what we did was we used a potential field source surface model to figure out where the magnetic field lines should be in the corona. So this is a model which takes the photospheric magnetic field and extrapolates it into the corona by assuming that there are no currents, which is a reasonable approximation in things like coronal holes and quiet sun regions, and becomes less of a good approximation in, for example, active regions. But for our purposes, it should be quite accurate. Okay, so this is showing where the magnetic field lines would go through our ice observation. And so here's the observation itself. In this case, I've plotted the temperature we infer from the spectrum. So this is a temperature map is the color scale, and I plotted some of the field lines that pass through our data. So you can take every pixel in here and figure out the field line that would pass through that pixel in the plane of the sky, and then trace that field line through the rest of the data. And what we could do is we can take the non-thermal velocity in every one of these pixels and trace it along the field lines. Now, there are some potential line of sight issues with doing this. So we have adapted some criteria to try to reduce those kinds of problems. So the first criteria is we remove heights below about 1.05 solar radii. So that's because close to the surface of the sun, you can have small loops which are a bit more randomly oriented and hard to capture with this PFSS model that we used. And so you might have flows along the line of sight there, or you could have spicules coming out of the sun, and they would broaden the lines because of a flow and not a wave. So we cut those out. And we also remove large heights, because at large heights, you can have stray light from the detector. It can be problematic. And also the data is a bit noisier. So we removed that. And we remove pixels that are not isothermal. So we do a differential emission measure analysis, which is a kind of analysis that reveals the amount of material at a given temperature along the line of sight. And we remove pixels that are revealed by this analysis to be not isothermal. So the idea being that if you see two temperatures along your line of sight, then one of them in the foreground and one's in the background, and you don't know which one corresponds to the field line you're trying to map. So because you might have multiple structures there, it's a bit complicated, so we omit those pixels. We also, since we're looking for Alfvén waves, which are a kind of transverse wave, we want only places where the field lines are perpendicular to the line of sight. So we do not analyze any data if the field lines became more than plus or minus 20 degrees away from the perpendicular. In this particular observation, the field lines were very nicely kind of north to south, so most of them were satisfied, but there's another one in our paper in which this was something we had to correct for more. And also, even if they're off by plus or minus 10 degrees or something, then some of the field lines might come out of kind of the plane of the sky. So we expect the emission to come from mostly the place at the lowest height. So if we're looking in the plane of the sky, that point where the height is closest to the sun is the plane perpendicular to the line of sight that goes through the center of the sun. And away from that, the density decreases because the height is larger. And so if the field line comes out too far from this plane where most of our emission is coming from, then that field line no longer corresponds to our emission. So we would omit those data also from our analysis. So here's a plot in which I just show some of the points that were removed. So we removed these points for being too close to too low of a height. Maybe there's the spicule problems or the small loops. This area is a small prominence in which is not isothermal along the line of sight. So these pixels get removed based on the DEM criteria, and at larger heights, these points are removed from being at too large of a height. So maybe scattered light is a problem there. Then we do the same as before. We calculate the non-thermal velocity, and we determine the wave energy flux. In this case, of course, we get the mass from the proton mass times the electron density. This time, we get the magnetic field strength from the potential field model instead of from an empirical model. And then this also gives us the expansion factor because we know the magnetic field strength. And then we can determine the energy flux of the waves times the area. So here, yes?
These are closed loops, right?
Yes.
So the wave will go out and come back, or are you assuming that it's all getting dissipated at the top of the loop?
Well, I will come to that. I think we have some interesting results in that area. So if they weren't dissipated, then they would come back to the other side. Yeah, that's an interesting point. So this is a plot of the energy flux times the area versus the x-axis here is a bit funny. I've put the 0 at the top of the loop since there's one top and two bottoms, so it made it easier to figure out where to start from. And then the coordinate, so this is distance along the loop normalized by the loop length or the loop half length. And then I've reversed the axis because you should have the bottom of the loop on the left in order to make sense of it. So this is the bottom of the loop and this is the top of the loop. And there's a few different sizes of loops just to show that you get the same kind of trend either way. So again, we fit it with a function that's constant and then decays exponentially, and we see that this is a reasonable kind of thing to fit in most cases for these lines. And so the horizontal level, again, gives you the base energy flux, and then you get a point where the damping begins, and you get some exponential decay. So since we have many field lines and it's a bit difficult to plot on a plot like this, I'll show some histograms. So for every pixel in our data, we trace a field line, so that's why we have many field lines. So this is number of field lines versus the calculated base energy flux that we analyze. And so we see that it's around 4 or 5 or 6 ergs per centimeter squared per second. Now for quiet sun regions, the estimated amount of energy needed is about 3 times 10 to the 5 ergs per centimeter squared per second. But since this is a loop, you have 2 foot points, so you only need 1.5 at each foot point, and that's this line here. So we see that it looks like there's enough energy in these waves to heat the quiet sun. Then we look at the point where the damping begins. So this is a plot of the point where the damping turns on versus the loop half length. And I think this is one of the more interesting results, is that there's a pretty strong positive correlation between the point where the damping begins and the loop length. So if the waves were being dissipated by something like viscosity or resistivity, you might think that on whatever loop it's on, the wave is going to go a certain distance and then be dissipated, in which case this length would be a constant. Instead, we see that it is positively correlated with the loop length, so that the dissipation process knows about the length of the loop somehow. So maybe this is because the damping depends on the frequency of the wave, and maybe there's a resonance that depends on the loop length, and that could be an explanation. Another explanation is that because you have waves at both foot points and you launch them there, then when they get to the top of the loop, the waves are colliding. When you have counterpropagating Alfvén waves, they can generate turbulence, and it could be the turbulence that is dissipating the waves. So this could be just because the waves have to go further before they interact with each other on the longer loops. So it implies that the damping somehow depends on global loop properties, although we don't know exactly why yet. And then this is a histogram of the number of field lines versus the exponential decay length. And this is, I think, the parameter that has the largest uncertainty in this study, because we don't have too many points above the point where the damping turns on for the larger loops because of the limited field of view of the observation. So that's why there's this kind of quite long tail here. But for most of them, we would say that the damping length scale is 100 or 200 megameters, which is shorter than the lengths of the loops. So it seems as though basically all of the input wave energy gets dissipated in the corona, which suggests that the quiet sun is also heated by waves. So one of the questions that this raises then is, what is the physical process that causes these waves to damp? we've argued that viscosity and resistivity would not be fast enough. So what is? So the observed damping is faster than viscosity or resistivity predict. And the additional damping mechanisms are possible because of the structure of the real solar magnetic field. So one factor is that you have gradients across the magnetic field lines, and this can lead to processes such as phase mixing. So the reason that you have these gradients across the field is because the magnetic field originates in this kind of magnetic network. So what you see here is a plot of the convection cells and the magnetic field in the photosphere. So these black lines are outlining the edges of the supergranular convection cells, and the grayscale here is showing the magnetic field. So white is positive magnetic field, and black is negative, and gray is neutral. And you see that the convection pushes the magnetic field to the edges of the convection cells, and that's where all the magnetic field is concentrated, and that's called the magnetic network. So if you were to look at this from the side, it would look something like this. So you have a concentration of magnetic field in the photosphere, and then these, as you increase with height, the magnetic field lines expand until they're all bumping up against each other in the corona. So you have these flux tubes. Now, since they originate far apart, you could have a different plasma over here in this flux tube than you do in this one. So it can be a bit different in temperature and density and magnetic field strength. So you have a different Alfvén speed in these two flux tubes, and then they are next to each other here at this boundary. And so this can lead to phase mixing. So the idea here is that the phase velocity of the Alfvén waves is the Alfvén speed. So if we were to start off with Footpoint oscillations that generate waves, let us say, at the same frequency and initially in phase, then because the phase velocity is different in the two flux tubes, they will become out of phase after they propagate a little bit. So due to having the different Alfvén speeds. So this causes them to kind of bump up against each other, and it creates little eddies in this gradient layer, and this increases the viscous friction. So phase mixing is a way of basically enhancing the viscosity and resistivity, but by having small-scale flows in this boundary. You can also have increased dissipation due to the gradients along the field, such as due to wave reflection and turbulence. So this is how the Alfvén speed would look versus distance from in our observation. And so you have wave reflection if the phase velocity, the Alfvén speed, changes over length scales shorter than the wavelength. So if the waves are short wavelength waves, then they kind of adjust to it, although there would be some partial reflection. But if the Alfvén speed changes on a scale shorter than the wavelength, and it looks like kind of a discontinuity to the wave, and the wave gets strongly reflected. So this is kind of a way of trapping wave energy at low heights. So if we were to put that in terms of a frequency, then this frequency for strong reflection, which is big omega A, goes as about the derivative of the Alfvén speed with radius. So here's a plot of what that would look like. So this is actually using the full equation for this critical frequency. This would be a bit smoother looking. But what you find is that there would be some point at which high frequency waves could be transmitted and low frequency waves would be reflected. So there are estimates about what the photosphere should generate in terms of wave frequencies, and those are something like 100 to 1,000 seconds periods, or 500s to 5,000s inverse second frequencies. So if I was to plot some frequency that looked like that on this plot of the strong reflection, say this one, then that would make the wave be reflected about 1/10 of a solar radius above the photosphere. So the wave would come in and be trapped there. So of course I picked this particular frequency because that agrees nicely with where the dissipation turns on in my observations. But this is a plausible explanation for why they look that way. And also in loops, you would have this wave interaction automatically. So the reflection in the coronal hole would be necessary to trap the waves, but in, so I got a little ahead of myself. So if you reflect the waves, you get counter-propagating waves, and when you have counter-propagating waves, this is a condition for generating turbulence. And the turbulence causes energy at long length scales, our low frequencies, to be to cascade to higher frequencies and shorter length scales. And at those length scales, they can interact with the particles through resonances and in other ways. And so this is a way of actually not only trapping the energy, but dissipating it. And in quiet sun loops, you don't even need this reflection to occur because you have 2 foot points, so you naturally get counter-propagating waves. So there are some theories for coronal heating in which you assume that all the heating is due to waves, and then the only difference between coronal holes and quiet sun regions is that you have automatically counter-propagating waves in quiet sun regions, and you have reflection in coronal holes. So that's quite an interesting way of heating the corona with a few number of parameters. So okay, so we don't actually know which of these processes is the most important, and they're all rather theoretical, so there's not much data on how they work. So we would like to do some plasma experiments in a laboratory device to understand how these processes actually work. So we have proposed to do some experiments on this device called the Large Plasma Device. It looks like this. It's basically a 20-meter long cylinder in which you can make a plasma, and then you can launch waves in it and probe them with very high accuracy. And so this is just a picture of it, but I'll show a schematic on the next page. So this is the vacuum chamber here, and it's a big cylinder, 20 meters long. Each of these kind of vertical things in this schematic is the magnetic field coil, and you can control many of these independently, so you can make kind of whatever magnetic field you want. So in this case, this is from a paper where they did an experiment where they have the magnetic field at about 1800 Gauss, and then they drop it to 1000 Gauss here. And then you have an antenna where you can make waves. You can launch the Alfvén waves here. And then you have probes in the plasma to measure the plasma. And the way that you do this measurement is it's a pulsed experiment. The plasma lasts about 10 milliseconds. So you put your probe in, it's just an electrode to count the current or the flow. You can measure the temperature, the density, and the magnetic field strength. So you put your probe in the plasma where you want to make your measurement, and you take 10 pulses or however many you want until you've built up good enough statistics, and then you can move the probe however small a distance you want and then measure again. So you can get extremely good spatial resolution. It just depends on how long you want to collect data for, and so you keep doing this over and over until you build up a nice measurement. So in this case, what they had done was the antenna's here and the probes are in this region. And they started with a high magnetic field and go to a low magnetic field so that the magnetic field goes through the ion cyclotron resonance. So here they were looking at how the waves are dissipated when the Alfvén wave frequency becomes close to the ion cyclotron frequency. And then this is an example of the wave magnetic field. So you can actually measure the wave magnetic fields themselves. And this is the wave magnetic field in the y direction. So z is along the axis, and then y is one of the two radial directions. And so you can see that they measure this with very nice spatial resolution. Faster than the sun. So I will show that on the next page compared to the sun. So the reason we want to do it in this experiment is that in terms of dimensionless parameters, you can make plasmas that are similar to the corona. So here's the I didn't put. So the Alfvén speed relative to the thermal velocity is the one that matters, because that controls the Landau damping rate. So I guess I don't have the actual Alfvén, but if it's denser than the corona, and it's but the magnetic field strength is also larger. So I think it's some thousands of kilometers per second. Yeah. So anyway, so in terms of dimensionless parameters like beta, the wave amplitude, the Alfvén speed relative to the electron thermal velocity, the wave frequency compared to the reflection, the frequency for strong reflection, the system size compared to the wavelength, and the damping length compared to the wavelength. The conditions in the corona match what you can do with LAPD. The only one of these that's kind of close is this one with the ion cyclotron frequency, but that's actually not problematic because the resonance is very sharp. So as long as you're not within about 0.1 of the resonance, then you don't have any effects from that. So you can make it low like it is in the corona, and that's the main thing. So we can model coronal plasmas using this device. So among the experiments that we would like to do is we would like to measure wave reflection from a gradient. So we could set up a scenario that looks like that you have a high magnetic field and then a low magnetic field. So your reflection frequency would look something like this, and we can launch waves at these different frequencies and measure the actual wave reflection from a gradient. We think that this would be the first actual measurement of wave reflection from a gradient, as far as we know. We've come across papers in which people have put in like metal plates and things and watched Alfvén waves reflect from those, but there don't seem to be any experiments that have systematically measured changing the gradient or changing the frequency and seeing the transmission and reflection coefficients. So this would be a very nice test for theory. We can also study phase mixing by creating a radial gradient. So we would use a mesh with a varying transmittance when we fill up the plasma to create a controlled radial density gradient in the electron density. So something like this, just schematically. And then you would be able to look at waves in this gradient and observe the phase mixing and see what the actual dissipation rates are. And also, so sort of the linear theories about the phase mixing would say that it's not actually all that fast. You still need a couple of wavelengths to make the phase mixing really work. So maybe it's not fast enough to match coronal observations. But other theories say that in this gradient region, you can generate fast waves that will cross the magnetic field lines, and then they can have a resonant dissipation. So the dissipation rate may be faster than predicted from just pure phase mixing. So we can look for that experimentally. And finally, we can combine these things, which is the situation in the real corona, and see how they interact with each other and which one is more important. So the question then would be, do the damping processes add in a simple way, or do new effects occur? So some people say that if you have wave reflection and then you have this gradient, then the phase mixing doesn't really change, because all you're doing with having the change in the magnetic field is changing the wavelength, so that just changes how long it takes for the phase mixing to build up. So it's kind of a small effect, whereas there have been some numerical simulations of this that have said you could have a order of magnitude or larger increase in the dissipation rate from combining a gradient along and across the magnetic field. So then, in conclusion, Alfvén waves appear to carry and dissipate sufficient energy to heat coronal holes and the quiet corona. The damping mechanism is not precisely known, but it is likely driven by gradients in the plasma properties. And we're planning laboratory experiments to test the underlying damping processes. And then let me also leave with some open questions. So I discussed a bit what is the cause of the observed damping. So that's one open question. Another question is, what is the actual Alfvén wave mode that is being observed in the corona? So there is kind of debate about whether you're seeing the kink or torsional mode. So you have a flux tube, and a kink mode is one that moves the whole flux tube. It kind of changes the center of the axis here. And a torsional mode is actually the kind of pure Alfvén wave where you are moving the magnetic field within a magnetic flux surface. And the way that the energy is distributed in the flux tube is different for these two modes. And so it changes actually the amount of energy that you infer. So the simple estimate of the energy that we inferred using this rho times delta V squared times VA is valid for torsional modes, but it overestimates the energy in kink modes, and the amount that is that would be wrong by would be by what is the density contrast and the filling factor and things like that. So it could be a factor of a few. But other estimates say that there's about half kink waves and half torsional waves. So we think that the Alfvén waves would still do a lot of the coronal heating, but maybe you would need a little something extra depending on how many kink or torsional waves you have. And then another question is, what is the origin of the waves we observe in the corona? So we've talked about that they need to be, that they're generated by the convection somehow in the photosphere. But it's not exactly clear how you get an Alfvén wave from the photosphere into the corona. So if you actually generate the Alfvén waves in the photosphere, Alfvén waves are reflected at gradient, so they shouldn't really get through the transition region unless you have some resonances. So this is a large area of research is figuring out how to get the waves from the photosphere to the corona. So thank you for your attention.
Okay, we have time for a few questions. Any? Danae?
The test that we did was, well, we did the DEM using it was a very simple kind of DEM where we fit it with we saw whether you could fit the DEM with a Gaussian. And if the Gaussian was below a certain width, we said that it was isothermal. So there's a certain resolution that we believed we could result, that if you do the DEM, then you always get some kind of broadening. And if it was larger than what was consistent with being isothermal, then we said this is not isothermal. We threw it out.
On one of the first slides, you had a picture of the slit widths, the slit positions for the coronal hole on the EV image, and it looked as though the coronal hole was kind of small and not even really on the rim, so it would have had an awful lot of background from the color.
Yeah, so we did look at that also through a DEM analysis, which I didn't mention. But in that case, what we did was we used lines formed at low temperatures. So I think we used up to iron 11, and we determined from the DEM how much of that came from a temperature below, I think, 1,000,000 Kelvin, and how much came from a higher temperature. And so those were all dominated by the low temperature part of the DEM, and lines above iron 11 would have been, a lot of that emission would have been from the high temperature component of the DEM, so that's why we didn't use those lines. So that's how we tried to control for that, by using low temperature lines. And you do see that we get the same result for iron 9, 10, and 11, which are the things that are dominated by the coronal hole emission. So since those are all the same, we think that those were all from the coronal hole. If I don't know if I have it, but if you look at the plot for iron 12 or iron 13, the behavior of the line width with height becomes noticeably different. So there was a definite change between iron 11 and those lines. So we think that these lines are coming from the coronal hole.
Yes.
You have substantial reflection. Doesn't that mean that the effect you're measuring, you need to worry about whether it's an illusion just as a result of the reflection on the way out? And have you contemplated how that affects the result?
So I think that if the energy is trapped at low heights, then, and not necessarily dissipate, I think that if you have these interacting waves, then it's dissipated anyway by making turbulence. So are you asking if we could just have wave trapping and maybe not wave dissipation?
Exactly.
Yeah, so that's possible. I don't think that we would be able to tell the difference. But if you have the wave being reflected from some point in the corona and then probably also being reflected back in the transition region, then that energy is being trapped there and should eventually dissipate. I mean, this is kind of, we don't know, but it would make sense if the energy was still doing some heating there, because you would be generating a lot of turbulence. But yeah, we can't tell which direction actually the waves are going because we don't observe in time, so we don't actually see the waves themselves. So we measure the line width, which is from this transverse amplitude, which is the same whether they're going up or down.
You talked throughout about Alfvén waves. Is that an assumption, or can you actually tell these are Alfvén waves, not some parts of your MHD modes?
Well, they could. These kink waves are actually a kind of fast mode, but under the conditions in the corona, they're very close to. They travel at the Alfvén speed, and they're basically non-compressive. So when I say Alfvén waves, it kind of includes kink waves. Some people call them Alfvénic to avoid making a mistake like that. But yeah, so here and there.
Tell that these are incompressible waves?
We do not see any. Well, we integrate in time, so we wouldn't see the intensity oscillations anyway. But we don't think that they're. Some people have looked for compressive waves, and you do see some compressive waves, but they seem to be slow waves in coronal holes. So there's no evidence for much compression with these waves. And we do see that they are traveling at the, we have this fit of the line width versus height that follows initially this density to the -1/4 dependence. So that's what you expect for Alfvén waves. So I think that's some evidence that they are Alfvénic waves.
The damping mechanism can be quite different
Yeah.
between Alfvén and more longitudinal waves.
No further questions. I'll just announce that we'll be going out to dinner tonight at 6:30. Easiest thing to do is just leaving from my office in D403. If you're interested in joining, email me, rsmith@CFA, and we'll be happy to add you to the list. But otherwise, let's thank our speaker again. Right on the money. Nice talk.
Thank you.
The question I was going to ask was going to be ugly, but because it was going to take a while, was you're doing one-dimensional fits through the